Why do they actually matter? The macro optimizations we looked at earlier, 2 slides ago, they kind of lay the foundation for a performant application. So we need to make sure that this is also there. We can't just not do it and just do micro optimizations. We need both in a way. The micro optimizations, they can have a significant impact when they are combined and applied consistently throughout the code base, especially in scenarios where every millisecond counts, like real-time processing, or where the battery life is critical, like in wearables, or if the resources are severely limited, like in low-end hardware. For example, if your application is targeted towards emerging markets, chances are high that the average device that your target audience will use doesn't have, I don't know, 20 CPU cores available, right? 32 gigabytes of RAM. Most likely it will be more constrained. So micro optimizations bring a few challenges. All right, thank you everybody for joining, or I guess for tuning in to this side of the stage. My talk today will be about the impact of micro optimizations in large scale applications. So the way I like to do these talks is I start at an introduction level, right? So everybody can take something away from it. So first, who am I? My name is Damien. I'm a software engineer. I work currently at Meta. I work on the WhatsApp product. And I'm based in Berlin, in Germany. So I work remotely because we don't have a lot of engineering in Germany. I have around probably like 15 years of experience in software. I started in the early days with PHP, MySQL. In the good old days before object-oriented programming was a thing for PHP. Then I moved over to mobile applications when I got my first Android phone sometime after. Like now I'm also working again with PHP because in our company we use Hack, right, which is like our own PHP variant. So I do a lot of things in a way, but that's enough about me. So this talk is going to be about optimizations, right? So first, to give like a brief overview. At first, I just want to look at like what are optimizations and then what are micro optimizations, right? Then we will look a bit at resource optimizations. We will take another look at benefits of micro optimizations and how to measure them. So we will look at a few case studies of like large scale applications that implemented some of these micro optimizations and what they actually bring us. And then in the end, we will look at like a summary of best practices and what to look out for, how to approach all of this. So let's get started. The first one, what are optimizations? In a very basic sense, optimizations are techniques used to improve performance, reliability, efficiency, and scalability. So we will look mostly at the context of mobile apps, where a lot of this is about minimizing the usage of system resources while maintaining or improving the user experience. So the first one I want to look at is just resources, right? So if we are honest, you know, building mobile apps can be quite complex. There's a lot of challenges, especially with performance, because mobile phones and mobile devices are quite constrained devices, right? It's constrained system. So the phones are getting, okay, they used to be getting smaller and smaller. Now we are kind of on a growth factor again, like moving more towards phablets. But a few years ago, they were getting smaller and smaller, so we had to cram in more features into a smaller space, right? Even now, the phones have a lot of computational power, but they are still constrained, right? So even though we are adding more power, more computational power, better rendering capabilities, we are also getting more demanding, right? So we want higher frame rates, we want higher resolution, we want more connectivity, we want more sensors, we want pretty much everything in the phone, but it should still be like super small and very thin. So we are building our systems to accommodate for this. So in a nutshell, that means we only request data that is required at the specific moment in time. We can do some prefetching here and there, but it needs to be justified. We keep data in the local caches and databases. We keep it around just to make sure that things render fast, that our TTRC, the time to rendering content, is as low as possible. We are downscaling resources to reduce the memory footprint and the memory pressure. And we are optimizing computations by just choosing efficient algorithms and avoiding like endless loops over data that we don't need to do. We also defer computations. We are prioritizing urgent work that we need right now in the moment, just to make sure that if a user clicks on a button, something is happening and they're not just stuck without knowing what is actually going to happen, right? So these optimizations will make our apps more performant, reliable, efficient, and I added a few quotes, for example, about ANRs, app not responding. So usually when we are blocking the main thread, there's like an estimate of like 60% of one-star reviews on the Play Store that mention app crashes or freezes. Then about the UX, introducing like a 1-second delay can result in a huge drop in conversion rates. So it is important to make sure that our apps, well, don't crash and that they work kinda efficient. Then we also just look at the competition, right? For each app that exists, every idea we can come up with, chances are high there's already 1 to 1,000 in the Play Store, App Store that do kind of the same thing or a similar thing. So if our users notice our app is slow, it's crashing, it doesn't work as expected, they might just go to a competitor, right? That offers maybe the same thing without crashes. So if we break it down into types of optimizations, the first one would be macro optimizations. We will look at the micro optimizations in a bit. But first, what are the macro optimizations? These are usually high-level decisions that influence how we build our code, our software, how we architect things. It's, for example, choosing the right data structure, the right algorithm for our data structure. It's also just using an efficient database scheme with indices and all of the things we like and we need to make sure things are accessed fast. And then we also implement, for example, caching mechanisms, right? And we do this at like a high-level approach across the app to make sure that we can share all of this. These would be the generally larger decisions that impact the global data structure and the global data flow. If we move from that to micro optimizations, these are usually small-scale improvements. They are for a specific part of code or a specific system. And in the end, these can be things like bitwise operations instead of arithmetic operations, or minimizing object allocations, or garbage collection, or just optimizing graphics rendering. Just a few examples. There's a lot more of these that can be done, and we will get into that a bit later. So why do they actually matter? The macro optimizations we looked at earlier, 2 slides ago, they kind of lay the foundation, right, for a performant application. So we need to make sure that this is also there. We can't just not do it and just do micro optimizations. We need both in a way. The micro optimizations, they can have a significant impact when they are combined and applied consistently throughout the code base, especially in scenarios where every millisecond counts, like real-time processing, or where the battery life is critical, like in wearables. Or if the resources are severely limited, like in low-end hardware. For example, if your application is targeted towards emerging markets, chances are high that the average device that your target audience will use doesn't have, 20 CPU cores available, right? Or like 32 gigabytes of RAM. Most likely it will be more constrained. So micro-optimizations bring a few challenges. The first one is the difficulty in measuring the impact. We would be focusing on small improvements in very isolated code path. And while we can often measure this in a purely numeric way, it can be hard to show the actual impact on user behavior and on our KPIs in the end. So it's hard to test them locally, for example, on an emulator, because the environment will often vary depending on, like, if you use an emulator on, for example, the host system load or other parts like network connectivity. So there's too many variables in this equation. So another thing is that with the micro-optimizations, the benefits may actually appear in other parts of the application that you didn't actually touch. So for example, reducing the amount of objects we are allocating, or just making sure that we actually free up memory just when we don't need it anymore, can also reduce the amount of out-of-memory errors in completely other parts of the application, right? Because the overall memory footprint is lower. So we need to have like a holistic view when analyzing the impact and results of our micro-optimizations. Then on the other side, there's maintenance overhead. If we take it a lot, like very deep, like for example, what I mentioned with the bitwise operations, probably a lot of us have seen code that is full of bitwise operations. It can be a bit hard to read at first. You need to spend more time on it. The complexity is increased and it's harder to maintain this code. So the debugging will also get harder. In the end, we don't want to end up with, I'm not sure if people know these kind of things, right? There's like for Perl, I think, these competitions to create like the most concise piece of code that is in the end just hashtags and some plus signs. That's not what we want, right? We want to optimize our code, but we want to make sure that it's still maintainable and debuggable. So in the end, what we can rely on as well here is the compiler. The compiler is smart. It will kick out stuff that you don't need. It will inline stuff where needed, where it can. So we don't need to replace like variable names with emoji or with like single characters, right? That's not an optimization. That's something the compiler will take care of. So a big part is to make sure that our code is still maintainable and debuggable. So the benefits of these micro-optimizations, they are usually cumulative. So they are adding up, and the more of these in the more critical paths of the application or the code base you are doing, the larger would be the benefits. So it's, as I said earlier, right? Like the isolated impact might not be that easy to spot, but usually in like the big picture and like a more holistic view, that's where they shine. Then we will get like reduced latency, right? We are optimizing most likely our critical code path, and that results in just our users progressing faster. We are saving resources. Things will just be more responsive, right? That improves the user experience in the end. And another side effect that a lot of people would also like is better battery life. I mean, a lot of people complain about battery life, right? If you have an app that is draining your battery, that's not nice, you know. The phone will just die after half the day. That's not what we signed up for. So this is also one of the benefits of these micro-optimizations, where we just make sure that we deallocate things, we are focusing on the critical path, and we don't let's say, we don't waste resources on a constrained system. And there's a lot more of these benefits. If we go back a bit and we look at large-scale applications, there's a few more benefits that pop up. So imagine you're working on an application that is used by a few billion people every day. The chances are high that that you already saturated most of the markets that have high functioning, like high-end devices. And if you want to broaden your reach and in the end create access and enable access, the micro-optimizations can come in handy. Because as I said earlier, right, in for example, emerging markets or just on low-end devices in general, it could be that your application works perfectly on a high-end device, and that's great. But then if you try it on a 10-year-old Samsung device with a lot less computing power, it could just crash. So these micro-optimizations also bring a benefit of just enabling more access for other people. So it's opening up the doors, right? Maybe the experience is not as shiny, we have to disable some animations, we have to downscale things, but at least they can use our app, right? They can participate. Yeah, so that's, I guess, both points here, right? Like enabling access and also just increased adoption. Because if you have saturated your main market, but you still want to grow, you still want to grow your user base, then you don't have a lot of options besides growing into places where you're not that present yet. And chances are high that these optimizations could enable that from, let's say, from a technical perspective, not talking about marketing or anything else. So the benefits of this, of the optimizations, they can be measured with a lot of performance metrics. In the end, all of this depends on which metrics you want to measure, how deep you want to go, and what your data infrastructure looks like. The obvious ones, I put a few ones on the slide here, like load time reduction. Like if the content is just rendered faster, usually it leads to more user engagement, right? More user retention. Like nobody wants to wait 10 seconds for an image to load or for something to happen after clicking on a button, right? Then battery life extension. This can also lead to more daily active users, because in the end, if it's one of the main apps that people use, then just keeping the battery alive longer means they can come back later. Like they are not running out of battery, right? So they don't have to go home, plug in the phone and wait for a bit. They can just, use the app, which is nice. It also increases customer satisfaction. And then data savings is also a big one, especially if we look at, again, like emerging markets or places or just like areas where people don't have a lot of data. Like they don't have unlimited, they don't have a flat rate. This is also where like a lot of other aspects come in, right? Like some ISPs go into collaborations with companies to offer like that it's part of a flat rate, so it doesn't count against your actual quota. But these optimizations also help a lot, because we will just make sure that we are only requesting data we need. We will downscale things. We're not requesting like a 50 megapixel photo if we only have like a 4K display. So all of this will in the end increase the satisfaction of our users and make sure that people can actually use our app. So looking at the metrics a bit more, a few common metrics would be execution time, just measuring how long does it take to actually go through our code. Then the CPU usage, we can look at things like how many threads are active at a given time, how many threads are competing for resources, why are our threads stuck, which one is blocking, which one is taking up the most time. Then memory allocation, the classic, are we keeping, let's go back to the images. How large are our bitmaps that we have in memory? Are we actually downsampling them, downscaling them? Or do we do like, if we parse like a network response and it's like a quite large one, do we have an efficient way of doing that? Or are we allocating space for the same object twice? Like to parse it, let's say into a string and then JSON, something like that, right? So the last one would be, that I have on the slide at least, would be power consumption. We can just figure out like how much power is actually our application using. Like we can look at wake logs, how many times is our app waking up the device, how many times is this being done without an actual reason, without like something that is actually latency sensitive, that needs to be done right now, compared to something that could be done later when maybe the user starts the app, brings it back to foreground and pays attention to the app. I'm gonna dive into the execution time measuring for a couple of slides, just to give an example of how this can look. So if we look at the execution time, in the simplest way, this just means we will collect 2 timestamps, right? We will collect one at the start and one at the end of our code path execution. And then we will just take the delta. We can do this on test devices. We can do this on production environments. The test devices can provide initial insights, but executing these measurements in production usually provides a lot more detailed and fine-grained data. Because in the end, our users are not using the test devices, they are out there in the real world, and this will just give us better insights. But since we are kind of touching the system, we are trying to observe, we also have to make sure that we don't do it too much. So we need to sample our data collection as well. We have to make sure that, okay, let's take a look, like maybe we don't need 100% of the traces, right? We don't need to know 100% of the times how much time it takes to go through the code. Maybe it's enough for us to measure this on 50% or on 20%. It always depends on the variability that you have in the execution time and also on the amount of users that you have. So how this will look in a code, it's, like in the end what I just said, right? We will just take the start time, we will perform our operation, we will take the end time, and then we calculate the delta. That's our execution time. In this example here, we are not using any framework, we're not using any specific class or anything. We're also not storing it or doing anything with it. It's just an example to show like, what exactly am I talking about, right? When I say execution time of an expensive operation. if we want to take this into real life, this is, for example, what it could look like, right? So we have a function to send a message, and this function does a lot of things. It's quite rare that this function or the critical path we want to observe only does a single thing, right? So we would, for example, save a message to our local database to make sure we don't lose it on the way. Then we would schedule or we will schedule sending this message to the server. And then the last part could be that we update our view state in however this needs to be done. If it's a signal, if we do it right here. And in this example, we would collect the delta, the execution time across all of these at once. So this will give us insights into how long the critical flow takes. But let's say we see a regression. It's increasing by 10%. Then we look at the code, we see, oh, okay, we are doing 3 operations here. Which one is now the culprit? Yeah, we don't know. Okay. So if we want to dive in a bit deeper, things will get a bit more bloated. Suddenly I'm injecting a class into this class that is called performance logger. That is not something available, so everybody has to implement their own or use an existing framework or library for this. In my case, what I'm doing is I'm starting a trace. I just gave it the name send message, and then after each of these steps, I am just marking a point in this performance logger. What we get from this is, if we have the same regression in our send message flow of, let's say, 10%, we look at the data set and we look at our graphs, and now we can maybe identify, unless it's a very even distribution, which should not happen, we can identify which of those 3 actions is actually regressing. Is it saving the message to the database? Are there some logs or some waits or something somewhere included? Is it setting the message up for transfer to the server? Or is it updating the view state? So this will give us a lot more fine-grained information. So once we have this collected metrics, it's time to analyze them. So what we are doing usually is we look for trends, we look for patterns, we look for changes over time, because these can indicate regressions or a change in user behavior. So what we can look here is we can group this by things like device types, network conditions, by any environmental factor as well, just to make sure that we identify anomalies and outliers. And just to get like a feeling of, is this more happening on specific device types, or is it like across the board, right? Because if you work with Android, there's a lot of device types. We have foldables, flippables, we have a lot of them. So it could be that this just happens on like specific devices. And then to make sure that we actually get a good grip on this and we don't have to dive into the numbers every single time, let's visualize it. Let's set up a dashboard, let's set up a graph, let's figure this out over time, let's have a nice overview. We can make our lives easier here as well. So once we have this set up, we have to read the metrics. So usually what we can do is we look for bottlenecks, we look for insights into critical user paths. Here we would, in the basic example, we would look at the average execution time. A high average may indicate a bottleneck in the code path. We will look at the standard deviation. If there's a large standard deviation, so that means our metrics are kind of fluctuating, we don't have a very concise confidence interval, but instead it ranges from, let's say, plus 20% to minus 20%. This can indicate a high variability in execution time, and we might need to dive in a bit deeper. So we can just, for example, add more points, to figure out which part of our code is variable, which part is more deterministic in the execution time. And then we look for correlations. There can be correlations between the metrics, such as execution time, CPU usage. We look at the amount of active threads that we have in our system. All of these can help us to identify potential bottlenecks. And if we have good tracking for all of this, for like the active threads, we know which thread is responsible for which part of the system. All of this will help us identify, okay, so the device is busy because of this operation, while the user is trying to do or go through a critical path. And all of this will allow us to dive in deep and to figure out how we can improve the situation. So once we have a lot of data, it's time to look at distributions and patterns. So when we look at the average, we would look at P50, right? We would look at the middle. That's like the average, let's say, execution time that our average user has. But while this provides good insights into like the overall stability, there's more to it, right? There's also P95, which would be like the worst, or not the worst, but the slowest 5% of our users. If we compare the 50th and the 95th percentile, we can understand the spread of execution time. We can figure out if it's something that is on our side, maybe it's server side, right? And that doesn't depend on the actual devices. Or maybe it's something that is done on the client, on the device, and there might be something we can improve. So if there's a large gap, this could indicate that there's a bottleneck that affects a small percentage of users, but has a significant impact on these users. In the worst case, it could render the whole app useless or non-functional for the lowest percentile or the highest. So based on the analysis, we can look into a few optimization strategies to improve our execution times or the app performance or whatever resource we are looking at the moment. If we focus on the worst case scenario, P95, we can ensure that the majority of users experience a good performance, right? It would be 95% of the users, that's a good chunk. If we optimize for the average case, we will improve the overall performance as well, but we need to be mindful of the impact on P95 as well. If we use techniques like caching, parallelization, and lazy loading, which can reduce the execution time, it's important to also look at how this impacts the P95. Because things like a higher active thread count or just higher usage of these resources in general, they can speed things up for the P50 user, but they can slow down things a lot for the P95. So to validate the effectiveness, we will have to use A/B testing and experimentation, because we need to be able to compare both sides of the coin to each other. So we would create multiple versions of the code with different optimizations. We will test each version with a subset of users. We will collect the data, measure the impact, and from there we will figure out which one works the best for the sector that we are looking at right now. And we will also, of course, make sure it doesn't break our guardrails and that the app still works. So here we will use some, let's call it statistical methods. We need to make sure that our results are statistically significant. That usually just means we need to have enough data to make sure that our confidence interval is small enough to be able to say, hey, this is an actual improvement. It is real. The numbers show it. We have all the users that prove it, right? In the end, the too long didn't read of this section, and I really have to speed up, is optimization is an ongoing process. It requires continuous monitoring, continuous improvements, and iterations. So good steps here are setting up a dashboard. Could be for the whole app, could be just for your feature, for your product part. Use alerts, use notifications, be able to detect changes and regressions here, and regularly analyze and review the metrics, especially for the core, the critical path. And well then, from there, continuously iterate. So if you look at a few real-world examples, I can't go too much into actual product details here, so they are a bit simplified, a bit more generic. But some of these might be found in a lot of applications in the world. The first one is a simple parallelization of asset downloads, right? So we would be moving from a sequential download to a parallel download. And if we think about it, the primary effect would be a better utilization of device capabilities of the hardware, faster rendering. And then the secondary effect would be suddenly we might have a higher thread count. This can lead to increased stress on low-end devices. So if we only look at the average user, everything might look good, green, positive. But then if we look at P90, P95, we may start to see regressions, and we would be wondering, where are they coming from? Well, in the end, they come from us using too many of the resources we have available. So we have to put guardrails in place for a lot of these optimizations. We have to just focus as well on limiting it, making it a bit more specific for the device that we have, for the users. Do not just apply like a blanket solution to a lot of them. In this case, we could just use limited parallelism. We can figure out how many cores does the CPU have, what's the general active thread count in our application, and from there we will just say, okay, in this case we would just use like, let's say 2 parallel downloads. Here we can use 4, 8, Also depending on if it's a download of a resource, the actual network connectability, right? Or connectivity. Then the next example is layout improvements. So this is about the Android View world. It's not composed yet, so it might not apply to a lot of people here. But just an example of a grid layout that in my case, or in some case, let's say, had a lot of items, and you would think, okay, the views are being recycled, everything is nice, performance should be good because the views are small, they are not nested, they are very, very flat. And we switched this in an experiment to linear layout. So what this brings us is the linear layout has actually less individual views, but the views will be more complex. So the primary effect here was improved scroll performance all of a sudden. The secondary effect is the view inflation time increases slightly due to increased complexity. But here the layout optimizations are also important to just make sure it's extra flat, the hierarchy, not very bloated, and offloading the binding to a background thread. So this was just an example to visualize it. The original layout, let's say, in the actual example it had around 8, 9, 10 items per row, depending on the device's screen. And we noticed that on low-end devices, so P95, there is a very low scroll performance. So after a bit of experimentation and refactoring, we ended up with a different layout that looks more like this. So each of the outer squircles with the crosses in the background would be like a view holder. So it moves from a grid to a linear layout. And suddenly we have a lot less view holders and active views in the recycler pool that we need to care about. We, instead of, how many is it here? It's 6 times 5, so like 30. Here we only have 5. So it's a lot less, right? But then the views become more complex. So it was questionable if this will actually be an improvement or not. So we ran it as an experiment. We figured out scroll performance is a lot better in this approach. And the time to rendering is also better actually. So it was all over just a win. We did some optimizations here. So we did some optimizations here as well on the data pipeline. Those probably also had an impact. Just batching the data earlier, making sure it's like exactly in the right format, not just one item, but batching it into like a group of items, right? But these are always very dependent on the application, on the use case, and where you're coming from. And this is exactly why the experimentation part is so important. Next example, also Android View, no compose here right now. It's ViewStubs. So imagine just a screen that is in like a very high volume area of your application and you want to show a NUX, a new user experience. We will add, let's say, a new layout. We will set the visibility to gone. It's not going to be laid out, not going to be measured. It's a conditional layout, so we don't always have to show it, just for new users. So here's like I shortened it a lot, but it's like an example of a layout, right? We have a few text views, we have a button, 2 recycler views, and then the linear layout on the bottom is the new user experience. It just shows like, hey, there's a new feature, you might want to try it, just, push the button, test it. And then just replacing that with a ViewStub led to very good improvements. We expected the improvements to be good, but I didn't expect them to be that nice. Like what this does is it shifts the inflation from on creation to on demand, right? So whenever the actual view is being shown, that's when the inflation of the view happens and it will be rendered to the screen. And it has a few advantages, also disadvantages. So on very low-end devices, it could be that the device will drop a frame when this happens in the on-demand inflation. But looking at the actual metrics, so in one of the cases I observed like an inflation time reduction of around 50%, and I didn't expect it to be that much, so there was a very nice gain, a very nice win. But this again always depends on the complexity, right? So if you just have a text view, it's not worth it to replace it with a ViewStub. But as soon as you have any nested or any lower, any complex layout, chances are high it's worth it. Also, just to remove it from the memory footprint, even though it's not going to be measured or laid out, it's still in there. With the ViewStub, it's just a ViewStub. And time is running out. I don't know if I have to hurry up or not. A little bit, okay. So this is another example. I'm just gonna go a bit faster. So application context. A lot of us know it probably, use it sometimes. We can access things through this handsome object. We can access directories for cache, for files, for databases. But what I didn't know before, deep down in the source code, all of these getters are synchronized with a lock, and the lock is shared across most of them. So every time you ask for the files directory, suddenly the lock is acquired from your current thread. And this happens for quite a few of these directories. So if you use the application context, if you want to access these directories on other threads, you might end up actually blocking your main thread just because you want to get the cache directory to, I don't know, store an HTTP response or store an image or something. So the too long didn't read of this is a lot of these functions are synchronized. So it's important to not overuse them, especially in a multi-threaded environment. And if we want to access these directories from a lot of random places, we can cache them, you know. We can just cache them somewhere and then reuse it. So best practices, focus on the most critical code path and bottlenecks. Use metrics, profiling tools to guide the optimization efforts. Implement optimizations incrementally and measure the impact. Consider the trade-offs between optimization and maintainability. And continuously monitor and refine optimizations over time. And then, in conclusion, the micro-optimizations look very small, they sound small, but they can have a huge impact on application performance, efficiency, especially the larger your application gets and the more broader your user base is. By understanding how to measure and analyze the metrics, we can identify opportunities for optimizations, macro and micro. And by applying the best practices and optimization strategies, we can improve the performance and the efficiency of applications. And then the last point, continuous monitoring and refinement are key to ensuring that the optimizations remain effective over time, because chances are high we are not the only one working on the code base. So we need to measure, we need to monitor and be aware. Thank you for staying on my channel. That's all.
Thank you, Damon. Thank you so much. Very insightful. I was asked if you're going, please, to post somewhere the slides. People ask for it, so if you just post it on Twitter, Blue Sky, whatever, the file with the slides, that's a good thing. Thank you so much.